Swayam Prabha. Digital India. Educated India.
Okay, so now, we were saying before, we have all our ingredients set, and we can start with the design. And the first design problem, we have to decide how much shall we pre-stress our concrete structural element. So if you go back to the slide number 2 of this class, probably you will see that the pre-stressing, we consider it as a was like an equivalent force, NP0. And this NP0 is the product of the pre-stressing action times the area of the tendon. So we have two quantities to choose. The first one, we have some, technological recommendations, I will say. In the code, it's stated that you cannot pre-stress at a stress higher than 85% of that equivalent yielding strength that we have defined before. You remember, we said is the stress to which the residual deformation at 0.1% does correspond. Well, that is understandable because you are applying a stress to your tendon. You don't want it to yield. Otherwise, you have already exhausted largest part of its capacity. So you leave yourself a certain margin between the pre-stressing and the yielding. So if you go back to the numbers that we had, and it was a FP01 characteristic 1580 times 0.85, it turns out to be 1343. Well, whenever you have to prescribe something, this is done by a skilled workman in the yard, generally with a jack, okay? Do not prescribe complicated numbers, because controlling 1343, you may have jacks with digital gauges, but somewhere I have also seen jacks with analogical gauges. And controlling 1343 with an analogical gauge, it's utopia. So prescribe 1300. It's like the dimensions, as you have seen, there are integer numbers. When you prescribe, for example, the stirrup spacing, use 10 centimeters, 20, 25. Sometimes you just use 12.5, but you know why? Because this size here is about 25 to 30 centimeters. So generally, if you go there and inspect on the site, the workmen sometimes do this and check that they have one stirrup here, one here, and one in the middle. So consider also that these are, sometimes the way in which you just, have a survey of your site. Okay. We speak about digitalization, but we have also to cope into the fact that sometimes most of the things are still done in a craftsmanship way. The other thing is, if your design is simple, the chances to have it constructed well are higher. If your design is complicated, the error is in the details. So just remember, make things simple. So for this reason, I said 1300. And what does it mean? It means that, okay, we are just a few percent less than what is there. So we are okay. The pre-stressing force, as I said, is sigma P0 times AP. But now we have a number for sigma P0, but we do not know AP. The other issue is that we do not know where our pre-stressing tendons are. We know that we have to place them somewhere on our cross-section, but at the moment, we do not know where. And when it comes to, determine where the pre-stressing tendons are, you see, if I put them here and the centroid is here, I have an eccentricity. So this means that your pre-stressing actions has also automatically a moment effect together with it. So this moment effect, how do we calculate? Well, we calculate as the force times this eccentricity, but still, this eccentricity, we do not know how much is that. So our design problem has two unknowns. How much pre-stressing area do we put, and where do we put it? Which, formula-wise, are AP and E. What we do also have to know is that now, for example, we assume that our element is a roof element, which will work in this condition here. And let us assume that it works under a span L, which is 12 meters. Okay. If you remember, the depth of this element was 50 centimeters, so half a meter. The slenderness, which is the ratio between the span and the depth, is 24. That is the typical size ranges for this number. So these elements work under slenderness ratio 20-25. Beyond that, there is really a technological limit. Remember that this is the span. So your actual length of the element will be a little bit more because you have to take into account that your support is not a point. You have to support on a finite length. So your support can be probably a region of 15, 20 centimeters. So your element will be probably 20 centimeters longer than. But this span is useful to us because we calculate the maximum bending moment, which is, this is 5.5, if you go back to your slides, is the self-weight. 5.5 times 12 to the square divided by 8. And there is this number, 99, okay? So now, what do? Well, we start writing the first checks. We are in the initial stage, and the initial stage, as we have said, we expect, what do we have? Well, I draw a rectangular cross-section. We know that it does not like that, but it's okay. So imagine that you can schematize your cross-section like this. So you have your NP0 force here. If this is the centroid, this is E. And you have the moment due to the self-weight. This is your cross-section. So what do you do is to calculate the stresses at the bottom and at the top. At the bottom, what do you have? At the bottom, you have NP0, which is the force, divided by the area of the cross-section. Plus, I assume compressive stresses as positive. So this pre-stressing force is equal to a force, but also there is a bending moment effect. And this bending moment effect is compressive the bottom part of the cross-section and providing tensile stresses on the top. So I have the force plus the moment, NP0 times C, divided by the flexural modulus calculated for the bottom fiber. We have calculated it beforehand. Minus, because the moment due to the self-weight is opposite. So on the bottom part, it gives rise to tensile stresses. Minus the moment due to the self-weight divided by the flexural modulus at the bottom. So that is, solid mechanics formula, very simple for a flexural element. Well, an element under axial force and flexural. For the stress at the top, what does it change? The compressive force gives the same contribution because compressive force is uniform over the cross-section. The moments the moment you do the pre-stressing force on the top gives rise to tensile stresses. And the moment you do self-weight gives rise to compressive stresses. And you see that the sign here changes. This is minus, this is plus. What does it also change? The flexural moduli, because it's calculated for the top part of the cross-section. So this is a very, very simple, two very simple equations. Well, now you elaborate a little bit, you know what is NP0, you know what is and so on, and you end up with this. And you see that actually you have here two equations with two unknowns. The two unknowns are NP0 and E. AP, sorry, AP and E. So in a sense, you can say that your problem is at least well posed because you have been able to write the same number of equations as the unknowns of your problem. That is the first check that you have to make, because if you have less equations than unknowns, you don't know how to solve it. And if you have more equations than unknowns, your problem risks to have more solution and not be opposed. So you have two equations and two unknowns. But what do we have to compare these stresses with? Well, we expect that in this stage, the bending moment due to the self-weight is the minimum. We can expect that the action of the pre-stressing force is dominant. So we can expect compressive stresses at the bottom. So we compare this compressive stress with that limit that we have set for the 16 hours, because here, what we are considering, pre-stressing and self-weight, is when we have just removed the self-stress, the pre-stressing, released the pre-stressing and demolded. So we are at 16 hours, and this is the limit that we have accepted, 0.7 FCK at 16 hours, if you remember. What kind of limit are we going to set for the tensile stress? The tensile stress is at the top. Well, for the tensile stress at the top, we can say, okay, I don't want the structure to crack. So I set as a limit the flexural tensile strength of the material at 16 hours. You know, even if it does crack, it's not the problem, because these cracks will be on the top. And then you can expect that when you will apply all the other loads, there will be some compressive stress. This does not mean that the cracks will close, because the cracking is an irreversible phenomenon. But if you keep the stresses low, like here, we can expect that they close. Moreover, here we are going to apply a topping, and we are going to apply a waterproofing and so on. So that top part of the element will be protected in a sense. So these are the limits that we have set. Is that all clear so far? Shall we go ahead? Well, then I have to put some numbers here. My proposal is this, but you know, it's my proposal. The nice thing of a design problem is that you do not have a unique way of doing it. This is I propose to do. I can say, okay, let's try to, for one moment, then I will explain how, to fix the eccentricity, which is related to the position of the pre-stressing tendons. Let's say that it's 300 millimeters. Then I will explain you how did I end up with this number. So if I fix this, I will have two equations and only one unknown. And let's see what does it come out. If I put the numbers here, you remember 1300 is the pre-stressing stress. This is the area. This is the flexural modulus. You see the 1300 is the E. This is the moment due to the self-weight. So I have just put numbers into the equations. And I have put the limit stresses here. I end up with two equations. They are actually two inequalities, which, as you say, both of them state AP, so the area of the pre-stressing, should be lower than something. I have two values. And since what I get from here is an upper bound for pre-stressing. I have to select the lower number between the two. Which condition was this? This was the condition at pre-stressing release, where you have only pre-stressing and self-weight. And we have said the pre-stressing dominates. So this condition provides you an upper bound for the pre-stressing. You cannot pre-stress too much. This is what these equations are telling us. You cannot pre-stress too much because in the early ages, first of all, the concrete is weaker in a sense. But also in the early ages, you do not have enough gravity loads to counteract the effect of pre-stressing. So you risk to compress too much your concrete. And you see as I said, you have to select the lower between the two. The concept which dominates is that of the maximum compressive stress at the bottom. You cannot pre-stress too much because in the early stages, your element is working, let's say, under a negative bending moment, which cannot compress too much the bottom part. So that is what physically these equations are telling us. Besides giving us a number for the pre-stressing area, they are telling us this. Look, that your pre-stressing should not be too high, because you will say, okay, the more I pre-stress, the better it is, the better I can put loads on that. Yes, but there is a moment where all those loads are not there, but the pre-stressing is. So you cannot pre-stress too much, because at the very time zero moment of the structural life of your beam, you will have pre-stressing and self-weight, and the pre-stressing dominates, and you do not want it to exceed the capacity of your material. Yes. Oh, no, I thought that you were raising your hand. Okay. So between these two numbers, you select the lower one. Then we go for what we call here T infinite. Okay. At T infinite, what do we expect to change? Well, we expect that because we have added more and more gravity loads which increase the positive bending moment, we expect that the stresses at the bottom will be tensile and the stresses at the top will be compressive. But the stress equations, they are written in the same way, because we always have a compressive force, its moment effect, and the moment. In this case, it's due to all the permanent loads plus the variable load. So there is everything there. But there is another thing which has changed. Here I put, and it is not a misprint, NP infinite. In the previous case, I put NP 0. Pre-stressing force has changed. Yes, the pre-stressing force changes because we have what we call the pre-stressing losses. And we will see what they are due to, but for the moment, let's accept that they exist. Then we will explain what they are due to and how do we calculate them. But provided this, we write our equations. Now we have to set the limits. We set conceptually similar limits. Simply, the compressive will be on the top, but this time we accept 0.6 FCK because we are in the long term. And this is the flexural tensile strength at the bottom. Well, now in order to put the numbers, I make another estimate. I say my pre-stressing losses are 30%. It's a huge number. I say they are losing 30% of your force. We will see whether it's true or not. My pre-stressing forces are 30%. So my NP infinite is 0.7 NP 0. I put the numbers here. And you see here I get that AP must be higher than something. So I have a minimum area of pre-stressing. Yeah, I have to put a minimum pre-stressing because I have to counteract the effect of the loads. And if you end up with the numbers, you see that your range of values is not that high. You can be between 5 and 8 square centimeters. You have not much margins. We have said, okay, we will use 0.6 inches 7-wire tendons. You go to the technical fact sheets and you realize that the area of that tendon is 139 square millimeters. Just be careful. If you go and look the area of a 15 millimeter steel bar, that is 154. So the area of a pre-stressing tendon is not the area of the circle with the same diameter, because it's made of different wires. There are some, so remember always that. Then, okay, so this means about 1.5 square centimeter. And we know that we must be between 5 and 8, more or less. But we have another constraint. We have 2 stems. So we will put an equal number of tendons in each one of them. So we must have either 2 or 4 or 6. We cannot have 3 or 5. Well, if I put 2 of this, it's not enough. If I put 4, I am okay. If I put 6, I will be just a little bit higher than the limit. So you see, actually, we just have one choice, because the equations give you numbers. Okay, but those numbers then must be put into practice with what you have. And you have a tendon with a certain diameter. So your option is 4 of this. Now you have to decide where to put them. And these, you go to the codes, and the codes will tell you, okay, you are in a certain environment. We can imagine that we are in a factory, but there is no special aggressive process inside the factory. It could be a precast. It's a protected area, so cover 2 centimeters. Okay, but 2 centimeters, the code tells you the minimum cover is 2 centimeters, which can be this 20 millimeters. Then you must imagine that you have here, you will put some kind of stirrup. Well, the stirrup, the minimum diameter is 8 millimeters. This adds up. And then your first tendon, you see here, you have to consider that you measure them always from the center. So if it's 1.6 inches, there is other 8 millimeters more or less from there. So if you sum up 20 plus 8 plus 8, you get 36. Okay, let's say 40, you allow for some tolerances and so on. Then you also have some minimum spacing required between 2 tendons or 2 bars. Why do you have this minimum spacing? Well, you have this minimum spacing because, first of all, there is a region where the tendons interact with the concrete through bond stresses. And these bond stresses, we draw them as distributed, on the lateral surface of the tendon. But when they diffuse to concrete, they open like an umbrella. So there is a cone, a diffusion cone of the stresses. So you want to separate the tendons like the rebars, because you don't want this cone of the stress diffusion states to overlap too much. Because if you overlap these stress states, you might have locally very high local stresses. The other thing is that concrete is not a homogeneous fluid, it's a granular material. It contains aggregates. So you need to leave enough space for the largest aggregate to pass through. And generally, the code states that you must have at least a spacing equal to the maximum aggregate diameter plus 5 millimeters. In precast, we do not use generally for these elements. We might use maximum aggregate in the range of 15, 16 millimeters. Then depends on the national tradition, what are the size ranges according to which you go. We go by 4 because that is a transfer of the inch number of the sieves that you have for the aggregate grading, but 16 millimeters. So 16 plus 5 is 20. We must leave at least a spacing which can be twice the diameter of the tendon or of the bar. So I propose that here it's a matter of detailing, it's you. I propose that here 5 centimeter of spacing for easiness of, calculation. But what your E is, well, your E measures the distance from the centroid of the cross section, which was somewhere here, if we imagine, of the centroid of the tendons, because you put the pre-stressing action like a force, a unique force, but that force is due to 2 tendons. So that is the resultant of 2 forces, and you put it in the middle. So your E is like this. So if you sum up, this is 40 plus 25, which is alpha of 50, you are at 65 from the bottom. You remember what we said. This was our element. And we said that our centroid was at 128 from the top. It means 372 from the bottom. 372 minus 65 is 307. So that is where my initial estimate of 300 came from. But really, this is your choice. And you see here, there is no software, nothing. It's you that decide. And decide basically on the basis of easiness of execution. That must be your first requisite, because this is a matter of execution, of practical execution. Well, now what do we have to do? It's a little bit tedious, but we have to do that. Well, as a matter of fact, when we made our calculations before, we only considered the concrete cross-section. But in this specific case, when you release the pre-stressing, your pre-stressing will be a reinforcement. So it will contribute to your area. So you have to recalculate all your geometrical characteristics, considering the effective cross-section in which you add up the pre-stressing tendons, and you see the pre-stressing, well, these are the same as before, there is nothing. You see that what we have done here is to add, the contribution of the strands at level 1 and at level 2, which are at 2 different positions from the top. But we have applied this factor 6.5 here. Well, that is the way in which we do homogenize the steel to concrete, and is more or less the ratio of the Young moduli. Well, it should be 195 divided by 36. It's a little bit something like 6 point something. But for the sake of simplicity, I put 6.5. Okay, so you just go back through the same calculations. And what do we observe? We observe this fact here. This is the new position of the centroid. What has happened? It has just slightly shifted a little bit below. Yes, because we have added the contribution of the reinforcement, which is on the bottom part. So because of the lever arm rule, we must shift our reinforcement towards the bottom. Okay. The rest is just the same calculation as before. Well, you say, but for just 5 millimeters over 500, 1%, shall I go for this? Yes. We are structural designer. It's not that we are checking more or less. We are checking. So we must be precise. So you redo your calculations, moment of inertia, flexural moduli, and we reperform the checks. But at this stage, they are checks. Beforehand, we used the same equations for design. You remember, we didn't know AP, and we used that. Now we calculate the stress, and we check that the stresses are lower than what are the limits. And you see, this is, well, it's the outcome of the design, which has been, tuned to have this. You see, on the bottom part, which is the most compressive one, we have a compressive stress of about 12 megapascal. It's okay, we can accept up to 21, so we are quite safe. On the top, our stress turned out to be very slightly positive, 0.1, so it's really close to 0. So actually, here we are in a situation in which we do not even have a tensile stress on the top. 0.1 means slight compression, which is good. It's good. Well, remember that this is true only for the mid-span cross-section. Then what you have to do is that you have to check this for other cross-section. Generally, if you are where the pre-stressing is fully active, we will see later what does it mean. Since your bending moment is supposed to decrease, you will see that this check guarantees you also the others, but it's not so automatic. Now we have released the pre-stressing. Our element is there on the pre-stressing runway and is just slightly sagged up. What we do, we go, before we calculate, these are numbers that we keep for later. We calculate the stress at the in the concrete at the level of the tendons. So you see, we do not put here. Here we put the flexural modulus. We put here other flexural modulus, simply using the same formula, but you calculate the stress at a different position. It's like if you if you are with a rectangular cross section and you have the two tendons here and here, and your stresses, this is sigma, what we call it sigma C inferior. This is what we call it sigma C superior. And then you calculate the stress here, and then you calculate the stress here. Okay, why do we do this? You will see in a while. But anyway, you always use the same formula, simply calculating the stresses at different positions. Okay, keep these numbers there and store them for a while. Now we have to go to lift our element. And first thing that we have to decide is, where do I position my lifting hooks? Well, this is also a matter of design, because there are two issues that we have to take into account. First of all, as I said yesterday, imagine that you have to lift your element and you have your lifting hook like this. And here you are putting there are stresses here that act along that hook and are distributed by bond, but they are distributed, as I would say, in this way. So you have like that they progressively involve concrete. So you need from this point a minimum distance equal to the effective depth of the cross section. Now the effective depth of the cross section is about 400 something millimeters on either side. But while on the inner side of the element you have no problem, you need to stay clear from the edge. The other thing that governs the design is the fact that, you see, when you lift it, you are not supporting the element on the edge. You are supporting it on an inner position. So your bending moment diagram will be something like this. And so here you have a negative bending moment. Compression on the bottom, tension on top, which is exactly of the same sign, as exactly the same effect as the pre-stressing tendon. So while throughout the rest of the beam, the moment due to the external actions is positive and the one due to pre-stressing is negative, so they counteract each other, in this part here, they are acting together. So you do not want to go too much inside, because otherwise your moment will increase. But there is also another fact. In the initial part of the beam, also the pre-stressing, let's change the color. the pre-stressing force starts from here, but also distributes through bond stresses and distributes in this way as well. So in order it to be fully active on the cross-section, you must allow a certain transfer length or development length. So first of all, we have to calculate this development length. And it's based on a very simple model in which you calculate the equilibrium of the bar, okay? But if you go to the code, you find that you find this formula, which comes from that equilibrium equation. Is proportional to the diameter of the bar divided by 4. And you have the yielding, the design yielding strength of the steel divided by the bond strength. The bond strength is something that you can measure, okay? But it's also something that in this stage you need something to calculate it. You have a formula, which is this one. It's related to the tensile strength of the material. Why this? Because, you know, imagine that we have a bar, a typical bar for reinforced concrete has the ribs. But the tendon also have some, you know, undulated surface because there is this twisting. So if you are pulling this bar on this direction, these ribs counteract in this way. So this is the force that the concrete is exerting on the bar, which opposes to its pull out. If you look at the cross section, this is the bar. And these inclined forces will have a tangential component, but will also have a normal component. So you will see that if this is the bar is exerting a radial pressure on the concrete around it. And how this mechanism fails if you have the concrete around here? Well, this mechanism arrives at its failure because this radial inner pressure generates tensile stresses, and the failure is when you form these cracks here. So that is the reason for which the bond strength is related to the tensile strength of concrete. But so if you put the numbers here, okay, you find that you need a little bit, something like 100 bar diameters for full 100 tendon diameter for full development length, which turns out to be, in this case, about 1.7 meters. Well, I have decided, my design choice, to put the hooks at 900 millimeters, 90 centimeters. Why this? This is about twice the effective depth of the cross section. And it's about half of the development length. So I am at a balance between allowing enough space for the diffusion of the stresses and also allowing enough space for the pre-stressing to be distributed, because at half the development length, I can expect to have half of the pre-stressing active. I use a proportional diffusion law. Now, the hardest part is to cancel. It stays on the screen and not on the slide. Okay. So I make the check at 0.9 meters. So you see the bending moment is 5.5 times 0.9 to the square divided by 2. This factor here, 1.15, is the amplification lifting coefficient. Also, this you find in the code. When you lift, you are applying like a dynamic action. So you slightly amplify the value. It's not a static load, it's an amplification factor. And what you see here, you perform once again the check. You know, the equations are always the same. You always use the same fundamental equation of the solid mechanics. Simply, we change the position where we make the check, and What is interesting is that, okay, the compressive at the bottom, the compression at the bottom is still okay. But we observe that with respect to what we have seen before in the mid-span cross-section, also at the top, we had slight compression. Here we have a tension. Here we have a tension of 1.5 megapascal, which is still in the limit because the limit is 2.6. But we have tension. And, you know, having the tensile stress lower than the tensile strength, okay, you can say it's not cracked. But you cannot guarantee that there is really no crack, because you might have some shrinkage cracks, or you might have that the stress state sums up to some temperature deformations and so on. So you might form some cracks, local isolated cracks. But this check guarantees you that you will not have very high tensile stresses. So whenever you will come back and apply other loads, these stresses will gradually be zeroed, and you can expect your cracks to be closed or brought back. Okay, so see that the lifting, the state check at lifting was more severe than the state check at pre-stressing release, because our element is working in a different configuration. Now, the element, the element has been lifted, has been stocked, has been relifted, put on the truck, transported, and so on. So we are ready to evaluate it in the time infinite, in its structural design situation. And in order to do this, we are moving from the time zero towards service life, we are moving towards time infinite. So we have said there are pre-stressing losses. Okay, there are pre-stressing losses. How do we calculate that? The pre-stressing losses are mainly due to the long-term losses, mainly due to three main causes. The first cause is the steel relaxation. Well, all the solid material are viscous, have a viscous component in their behavior. What does it mean, viscous? It's like creep of concrete. Is that if you apply a stress, they continue to deform. But there is also a dual aspect of creep, which is the relaxation. When the pre-stressing steel is embedded with concrete, it's not experiencing a constant stress. It's rather experiencing a constant deformation, because it's the concrete which freezes it in that situation. When you have a constant deformation, over time, what does it happen is that the stress which is needed to keep this deformation constant gradually releases. So this is the relaxation. In steel, it's due to the fact, steel is not a molecule. You cannot write the chemical formula or the chemical graph of steel. Steel has a crystalline reticule, which is made of crystalline planes. Well, these planes, where they are under constant state of stress of deformation, they tend to slide along each other, to slip along each other, and align along the stress state. Because while the bonds between the carbon and the iron atoms in the plane are very strong, the bond between the planes of the crystalline reticule are weaker. So that is the reason for which they slide with respect to each other. So this is the microstructural cause of relaxation. And nowadays, we produce steel for pre-stressing with controlled relaxation. The tests are done at 1,000 hours. So 1,000 hours is quite a lot, because one day is 24 hours. 10 days is 224. So it means that you need 42, 45 days. So you have a tendon which stays there for 1 month and a half, a little bit more, something like that. And you record, you keep under restrained deformation constant, and you record how the load that is required to keep this deformation fixed go into time. Why 1,000 hours? Because it has been observed that this is a limit after which the relaxation stabilizes, does not decrease too much significantly. And nowadays, most of the steel for pre-stressing tendons that we produce stabilize over a pre-stressing loss, which, as you can see here, is 6.55%. This is a data that comes from the steel manufacturer. You can prescribe tests. You say, okay, I want to check it, or you can just ask for the certificates, the official certificates from the official lab of the test. So from the 1300 that we have applied, we already lose 6.5% due to steel relaxation. Then the other two reasons for pre-stressing loss are due to concrete. And they are both long-term, even if one of them occurs, most of it in the short time, and the other one goes on. They are due to shrinkage and creep. You know what shrinkage is? Because of hygral exchanges with the environment, concrete tends to reduce its volume. But you imagine you have your tendon, which has been pre-stressed. You cast the concrete, you release the tendons. From that moment onward, the concrete and the tendon will experience the same life. They will be bonded. So if the concrete tends to shrink, the steel also have to follow it, but steel does not shrink. So the only way for steel to shorten is to give it back, to lose some of its initial stress. And how do we calculate the loss due to shrinkage? Well, we have either experimental data, or we have formulations in the code which allow us to make some kind of prediction. We have the value of concrete shrinkage. CS stands for concrete shrinkage at time infinite. This number here, well, this has been calculated for that specific concrete. You know, when you have very high strength concrete, the shrinkage can be lower than for regular concrete. What is thus change is that shrinkage is composed mainly of two parts. One is drying shrinkage, which depends on the hygral exchanges with the environment. The other one is autogenous shrinkage, which depends on the fact that if you sum up the volume of the reaction constituents of the reaction products are lower. So there is this autogenous shrinkage. In high strength concrete, while in normal strength concrete, autogenous shrinkage is very, very low and is negligible, in high strength concrete, it becomes more and more important. This is a number, okay, is 0.28%, very, very, very low. This deformation is the shrinkage of concrete, okay? But we have said that from the moment that we release pre-stressing, shrinkage and steel, concrete and steel, experience the same life. So if concrete shrinks, steel will follow it with this deformation. So this deformation, because of bond, will be exactly the same deformation as of pre-stressing tendon. So if you have the deformation, you multiply by the Young modulus, and you calculate the stress. And you multiply by the area. Well, here is AP over 2 because we have tendons on 2 levels, bottom and top. You multiply by the area and have a force. So this is the amount of the force that you lose at each level because of shrinkage. Then there is creep. Well, the mechanism of creep is a little bit different from that of shrinkage. It's still due to exchanges, but the main difference is that while shrinkage is a deformation, sorry, I have to tie my shoelace, otherwise it risks to be. Okay. While shrinkage deformation occurs without any stress, shrinkage, if the element is free to shrink There is no stress. What is dangerous if you restrain shrinkage and then your element would like to shrink and restrain, keep it fixed, and you have tensile stresses. But shrinkage deformation is a no stress deformation. To have creep, you need stress. If you have no stress, you have no creep. So the creep deformation is related to stress. And what creeps? What is creeping is the concrete. So that is the reason for which we calculated the stresses at the level of the first tendons and at the level of the second tendons, because there we want to see how much concrete is creeping. So we have the stresses you see here at the first level and at the second level. We divide by the Young modulus of concrete. What we obtain here? We obtain here the elastic strain in concrete. We have said under certain stresses, the creep strain is proportional to the elastic strain. And the proportionality coefficient is this number here, phi infinite, which you can test, you can calculate. You see, we have assumed here, well, it's generally between 2 and 3.5. We have used a 3 here for this type of concrete. So the creep strain can be 3 times as much, twice as much, or something like that, as the elastic strain. So is the process clear? Calculate the stress in concrete. Divided by the Young modulus of concrete, you have a strain in concrete, and this is elastic strain. Stress divided by Young modulus is elastic strain. So this here is concrete elastic strain. If you multiply by the creep coefficient, we use the notation phi, the creep strain is phi times the elastic. So this one that I am circling in blue, this is the creep strain. Now you want to go from concrete to steel. So this creep strain is the one that concrete is experiencing, but because of bond, steel is experiencing the same strain. How can steel follow concrete in creep? Taking up some stress. Compressive stress, which reduces the initially applied tension one. To calculate this stress, you multiply by the Young modulus of steel, of the pre-stressing steel, which you can see here. Clear? I just cancel out this because it can be confusing. So we go from elastic strain in concrete to creep strain in concrete and steel to stress in steel to force, because we multiply by the area and we have the force. So in the end, you sum up the losses that you have due to steel relaxation, due to concrete shrinkage, and due to concrete creep. The meaning of the subscript is this: SR, steel relaxation; CS, concrete shrinkage; CC, concrete creep. You sum them up and you find this number. You see that they are higher at the bottom level because the concrete at the bottom level is experiencing higher stresses. You see, if you go and calculate your N infinite with respect to N0, you see that the ratio is 0.736. I estimated before N 0.7. That was a rough estimate, but at that moment, I didn't know how to do that. So, well, obviously I put 0.7 because I knew, you know, from experience, you know that the range is that one, 25, 27, 30%. More means that you are starting going into some non-economical way of managing, because we are losing 30%. So if you lose more, it means that you must handle probably a better concrete, which shrinks less, which creeps less, or to arrange your design in such a way that the creep losses are different. Because as you can see here, more or less, more than half of the losses are due to creep. The ratio here is more or less 20-25% due to seal relaxation that you cannot change. 15% due to shrinkage, 60% due to creep. So that is what you have to control. Well, at this point, you simply redo all your checks that we have seen before, but you put the true number of NP0 here. Is not any longer 0.7 NP0, is what you have calculated here after the losses. And your moment here will be the moment due to the self-weight plus the topping plus the waterproofing plus the snow load. So it includes everything. Still, we are here under the rare combination. So all the loads are with factor 1. Persistent means that what the structure will experience throughout the life. So this is the, it's not accidental or transient. Is the, it's opposite to transient or accidental. It in all the characteristic values for dead and live, all are there. And you can see here that the result of this are that if you check the stresses here, you see here we have a 2.9, this is at the bottom. Here we have a 2.8, this is at the top. So actually, our structure at mid-span, is like if it's uniformly compressed. So we are uniformly stressing it. Here you can also understand why making the check only here may not be sufficient, because if you move to another cross section, it's not only that there you are changing the bending moment because the bending moment is parabolic, but since you are changing the stress state, the pre-stressing losses will also change. So you have, when you design a pre-stressing beam, generally you have your worksheet tools that make the checks at different cross sections. For example, here is a 12-meter bar, a 12-meter long beam. Make the checks every 25 centimeters. So you have checks at different cross sections, because the bending moment will be different, but also the pre-stressing force will be different. First of all, because of the development length, and after that, because of the losses. So it's not that you check the mid-span cross section and go ahead with that. You have then to, work out a tool which allows you to make these checks at different cross section. What about elastic shortening? Well, elastic shortening, we have already implicitly taken it into account. Thank you for asking, because I had in mind to tell it. We have already implicitly taken it into account in doing this kind of calculation. We have already calculated the pre-stressing, not acting only on the concrete cross-section. We have calculated it on the wall cross-section. This implies that your cross-section is not 100% effective, is 100 minus the effect, because it's like if your cross-section is larger. So this accounts for the fact that when you release the pre-stressing, you have some initial shortening. This is the way to account for it. And in some textbook, you find it as an instantaneous tension drop, which is the way in which you fictitiously or practically, I will say, take into account the elastic shortening. Okay, so far, what we performed are checks. We used elastic stress equation. So these are for serviceability limit state checks. We have ended up with the fact that concrete generally does not crack, so we can use these equations. But we have not to forget we have not to forget that at ultimate limit states, the cross section of a reinforced but also a pre-stressed concrete element works at a completely different way. And at the ultimate limit state, the pre-stressing tendon is a reinforcement. So you will calculate it, you will check it exactly as you will do for a reinforced concrete cross-section. So here I draw a rectangular cross-section. And which are the assumptions? Well, the first assumptions that we make is that the Bernoulli assumption, the cross-section remains planar. We used to say planar cross-section equal to linear strain diagram. Yes, that is true, only if your beam has a straight axis. If your beam has a curved axis, and you can have in precast structure, you can have in timber structure, if the axis of the beam is curved, planar cross-section does not mean planar linear strain. It means that the cross-section remains planar, but the strains are logarithmic and nonlinear. This is something very important that you have to take into account. Planar cross-section assumption, which is the fundamental of the beam theory, means linear strain only if the axis of the beam is a straight line. If the axis of the beam is not a straight line, the planar cross-section does not imply linear strain. But we are in this case, the axis of the beam is linear, so this means linear strain. And this is the strain diagram. And you see we have compressive strains in the concrete. Then we have here tensile strains, whatever they mean. And we have put, it's a symbol, we have like concentrated all the area of the pre-stressing at the point, in the centroid of the pre-stress. At that level, because of the perfect bond, we know that the strain that we read on the concrete strain diagram is also the steel strain. So you see in this graph here, in this diagram here, there are already two of the assumptions of the reinforced concrete theory. Planar cross-section plus perfect bond. Then we know that ultimate limit state, we assume that concrete is cracked. So this tensile strain part is fictitious when we go into the stress. But we must associate to the strains some stress diagrams. Tensile concrete does not contribute. We assume that the pre-stressing steel is yielded. And so you see we have this FYD, whatever it is. And we assume for concrete the simplified stress block diagram. So uniform compression equal to FCD applied over 80% of the actual compressive depth. Are you familiar with this model? Okay. Mm-hmm. Okay, yeah. Well, also in yes, also in our Eurocode we have that, but we are allowed to use simplified stress block diagram. Just one thing, by the way, the parabolic stress diagram, good to point this out. Parabolic stress diagram, it's made in this way. And for concrete, this is 2 per mil, and this is epsilon Cu. Now, epsilon Cu is not a fixed number. Its value changes with the strength of concrete. For concrete grades, I think up to exactly C50-60, yeah, it's 3.5 10⁻⁻3. But then if you go higher with that, that starts decreasing. And for concrete C100, C120, it becomes equal to 2 per mil. So this number here, 0.8, is based on what? On the fact that this distribution here has the same area and the same centroid position as that one. Well, for the area, it's very easy to calculate because try to make this area here. This is FCD. This area here is 0.15 per mil because this is, let's say, 3.5 per mil, 0.15% FC plus 2/3 of 0.2 FC. 2/3 of 0.2, how much is that? Is 0.13 plus 0.15 is 0.28. If I draw this red rectangle, what is the area of this rectangle? It's 0.35 times FC. So the rectangle is 0.35, but the parabola is 0.28. 0.28 with respect to 0.35 is 80%. So keep this in mind that it's very interesting because the equivalence 0.8 is only valid up to C5060. If you go higher, that coefficient 0.8 starts decreasing and it will become at maximum equal to 0.67, 2/3, because when you reduce epsilon cu in the end, you end up only with the parabola and the area is 2/3. Okay. Oh, yeah, 0.8x. Yeah, surely, you are right. Yeah. Thank you for pointing out. Yeah. Let's rewrite it. Rewrite here. This is not this, but it's 0.8x. Yes, you are right. Thank you. More or less similar. Yes. Now, how do we calculate? Let's skip the first line for a while and let's go and calculate the 0.8x. So how do we calculate the maximum bending moment? Well, we write two equations. No need to remember complicated formula. Just remember that you have to write equilibrium equations, equilibrium of forces. First of all, write the force equilibrium. Which are the forces that you have here? You have the tensile force in the steel, AP F by D, and the compressive force in the concrete. With stress block, is very easy. It's 0.8 Bx FCD. But there is a but. This is a rectangular cross section. Our element has a cross section which is made like this. But we know that the concrete under the neutral axis does not count. So if you hypothesize that your neutral axis is within the 50 millimeter thickness of the slab, what is below does not count, can have the shape that it does want. So we are allowed to write the equilibrium as if it was a rectangular cross section. So if this equation is valid, it's a linear equation into x. You know, second year of middle school or something like that, third year of middle school, I don't know where. I studied in third year of middle school, I don't know whether it's the same now. Very simple, solve for x, and you put the numbers that are there, and you find 13 millimeters. So you see, the fact that you have this very wide area, you really need a very thin area of concrete. So what is, you know, in some codes you find that, for example, that this, if this neutral axis is lower than the maximum aggregate size, just use the maximum aggregate size, or instead of using 0.85 as a long-term factor, use 0.8. You know, you have some adjustment just to take into account that this is a very thin element. But anyway, that is. You have calculated the neutral axis, and you use that value to calculate the moment equilibrium equation. Well, here we are in the case where we do have a compressive force here and a tensile force here. So we just need to know either one or the other and multiply by the inner lever arm. And the inner lever arm is this one, D, the effective depth, which is calculated from the centroid of equivalent position of the tendons, minus, well, if this is 0.8x, the centroid is at half, so it's 0.4. And you end up with this resistant moment. This is what we, it's written also there, we call yesterday, we have seen MRD, design value, because we have all the safety factor of the material inside, design value of the resistant bending moment. What we have to compare it with? We have to compare it with this value of the bending moment here. This is the action bending moment. Well, it's still the loads multiplied by L squared by 8. But at the ultimate limit states, we have to factor the loads as well. So you see that for dead loads, the factor is 1.35. For live loads, the factor is 1.5. These come from the codes. Why the factor for dead loads is lower than the factor for live loads? It can be easy to be understood because, you know, live load is a snow load. I was giving you the example before. At a certain point in the Italian code, we had to change it because we never experienced a snow load so heavy. And so our snow loads were lower. When we experienced this exceptional snow load, we raised them. So there are uncertainties also due to the fact that meteorological, you know, loads, environmental loads, they depend on the return period of the action. And if you have never experienced an action with a phenomenon with a longer return period, you don't know. Then I will tell you also another story. Dead loads are more easy to control. They basically depend on the dimension of the element. But you can say, oh my God, is there that 35% of uncertainty I have in the dimensions of my structural element? Because that is just dimension, topping, and so on. I have a 35% uncertainty. Well, not. It's not only that uncertainties. Is the fact that, for example, when you lift your element and you put it on the supports, you may be most careful that you are, but you always have some boom dynamic factor. Then you put something to take into account also the size effect and so on. So that uncertainties, the uncertainties that we are not so skilled in quantify them, they go into this, you know, safety factor. So that 1.35 takes into account also this, takes into account tolerances, takes into account dynamic amplification and other things. With respect to the estimate of the, you know, environmental actions, let's call them like that. You know, one of the most difficult actions to estimate is earthquake one. Now we have very sophisticated, very nice geophysical models for wave propagation in soils. But I will say until 20 or 30 years ago, most of the seismic design codes were based on historical records. And in Italy, we have really a paradox. In region where my family, both my parents' family come from, in southern Italy, there is a river. Nowadays, it's a lake because they put a dam, so they created an artificial lake. My family comes from the left bank, no, the right bank of the river, because you have the, and yeah, they were, and the classification was based on administrative units. Okay, they were territories on both sides of the river, but really 5 kilometers apart from each other, One of them was seismic, the other one was not. That is contrary to any, physical intuition. And why was that? Because the classification was based on historical records. And which were the historical records, the most useful ones? Can you imagine? Most of the historical records based on which these estimates were made. It's not a critique, it's that it was done in this way. There were these estimates. Church registers. Or monasteries, because in monastery, the monks keep a diary. Today, this, and this happened, this storm come, and so on. Today, this earthquake happened. So how come that in one place they had that? Because in some cases with earthquake, the church registries got lost. Or you might have some fire and you get lost. So there were records which were missing, and that was the reason. Well, nowadays this paradox has been solved, but this is uncertainty. And there was this uncertainty. You have parcels of territory which were really very close to each other. They had a completely different seismic classification. It was just because of that. So this means that we have larger uncertainties in estimating this. But there is another thing on which now, let's go back to numbers, on which I want to draw your attention. So you see this number here, how much is that? 28.7. And this is 328. What is the safety factor that you have? Try to work it out, it's easy. 1.1, more or less. So it means that at ultimate limit state, you have a 10% with 1.1 safety factor. But no. So good. Let me clean this. So at ultimate limit state, we have 1.1 safety factor. Okay. Let's go to see what happened at the serviceability limit states. You see, we calculated a stress which was about 3 megapascal as compared to 30. So here at serviceability limit state, it seems that we have a lot of margin. When we go to ultimate limit state, we just have 10%. What has changed? The way in which the cross section is working. Here, you are keeping the wall cross section. When you go to ultimate limit state, what is working is the tendons and a very thin part of the slab. So it's the composite way in which the cross section is working that is giving you a completely different perception of the safety that you have. But what we have to bear in mind is that, okay, this safety check is still satisfied with a good margin. Also because never forget that we already have 1.4, 1.15 in the materials. And we also have 1.35 and 1.5 here. So if you factor 1.4 average with about 1.2 average from the material, 1.4 times 1.2, it's already 1.7, something like that. Plus you have the margin, the safety is 1.1. So if you factor this all, your effective is 2. Do never forget this. But also never forget that this is something that you design and you don't want it to ever happen. Serviceability states this situation here is what the structure is experiencing. And it's good that the stresses here are low because this controls the creep. One of the issues that you have in precast, pre-stressed elements is exactly the creep. They continue to creep. So if you keep the creep low, it's good because you do not have, you have this element, and if it sags too much, your waterproofing upstairs or your finishing upstairs, they crack. It creeps, but you have, we will see in the connection, you have seen also yesterday, never just put the element there and leave it to stay just because of self-weight and friction. You always have some pins or some steel profiles that keep it fixed. If the element creeps, it tends to rotate it tends to sag a little bit. If these connections tend to oppose to this deformation, tend to restrain these deformations, then you will have parasite stresses. So this is important to bear in mind. And there is one last thing that we have to consider, is shear. Okay, how do we check shear? Well, in the codes, we have the truss model. Okay, we hypothesize that there is a truss. This is steel, this is concrete, and this is the mechanism which is then superimposed and multiplied that governs the shear strength. Well, in a general form, the steel has an angle alpha and the concrete has an angle theta. Alpha, you design as a designer how much it has to be. Well, if we have steel roofs, alpha is 90 degrees, vertical reinforcement. But in the past, it was also used to have bent up reinforcement for shear, which in some cases can be more effective. Then if you go for earthquake, where your shear can alternate the signs, because you remember the diagram of the bending moment that Professor Aslan showed last morning for the moment in beams under lateral actions. But if the lateral actions comes on one way, you have this diagram of the bending moment on shear, and this is on the columns. But if the lateral action comes from the other way, the moment changes its sign, and so also the shear changes its sign. So it was realized that when you have this kind of actions, vertical steel roofs, they can function better. Otherwise, you have to put crosswise reinforcement, and as we will see in a lecture Monday, that may be complicated to achieve. So alpha is 90 degrees. What about theta? Well, in all design codes, theta came from the Morse truss, the first Ritter and Morse, because they worked it out independently at that time. You know, it was not easy to communicate, and so they are recognized the paternity of the method, both Ritter and Morse. The angle was 45 degrees. Why? Because Ritter and Morse did tests on beams, and they observed that when the shear was prevalent, the cracks were at 45 degrees. And why this? Well, imagine that, let's see if we can do something like this. How can I get a clear and show? Okay, insert. No. Oh. Oh no, enable in editing. Okay, yes. That's good. So new slide. Empty. Okay. Now let's go back to show. Let's go here. Let's cancel this. So as I was saying, Ritter and Morse observed, they did tests on beams like this. This is the support. There was a load here. So that your bending moment diagram is like this, and your shear diagram is like this. So in this region here, you expect to be shear critical. So they observed cracks like this, inclined at 45 degrees. And why is this? And most of all, they observed that whereas the bending crack started from the bottom and propagated towards the neutral axis depth, the shear crack started from mid-depth of the beam. And why was this? Well, this was because if you have a reinforced, well, it could be this, reinforced concrete cross-section under bending moment, what you do expect as stresses is something like this. And here is your neutral axis. This is compressive stress. This is tensile stress. And when this becomes larger than the flexural tensile strength, you form the crack. But when that same cross section is under a shear force V, the distribution of the shear stresses according to the Uraski formula is like this, with the maximum on the neutral axis, which is the centroid axis. So if you look at the state of stress at this point here, you have zero normal stress and only shear stress. So your state of stress, tau, is like this. And this is equivalent to a principal stress state, which is tensile here, sigma prime equal to tie, and compressive here, sigma second equal to tie, and this angle is 45 degrees. So that is the reason for which in the model that I drew before, which was this, steel and concrete, this angle alpha is at the designer, this angle theta, in the Morse truss model, this angle theta was 45 degrees. What has then led to use a slightly different model? Because it has been realized that over the years that, how to say, this led to a little bit too conservative design. So the actual load bearing capacity of the beams was much higher than what you could predict from here. So if your model estimates a lower bearing capacity, it forces you to put more reinforcement. And on one hand, you say, why don't I want to put more reinforcement? Why should we not put too much reinforcement? Eh? What do you mean condition? Oh, congestion. Yeah, okay, that could be that you want to avoid congestion, surely. So it's a technical reason, ease of execution for sure, yeah. Or what? Yes, that is over reinforced. So it's true that the steel is the ductile part of the couple. But it's also true that if you put too much reinforcement, your failure mechanism risk to go into the over reinforcement. So you do no longer exploit the ductility and you have a brittle failure and the steel is still elastic. The other reason is, as always, money, because putting steel costs. But which are the reasons for which the Moore and Ritter truss model underestimates? Because there is not only the capacity of resistance of this truss. There is also that when a beam is cracked, the cracks are not straight elements as we draw in the cracks in concrete are rough. So there is a mechanism which we call the aggregate interlock. Imagine that this is a crack and there are the aggregates which come out through the crack, and on the other face there are aggregates like this. So the crack goes through the aggregates. When, because of shear, these rough faces of the crack, they tend to slide with respect to each other, the aggregates oppose to the sliding. So there are forces which are exchanged along the cracked interfaces. And these forces sum up to the compressive force in the strut. So it's not only the truss mechanism, you have to add additional forces. So if you have a force in this way and you sum up another force like this, your resultant will be a force which is less inclined. So this is the reason for which the codes have introduced what we call not the fixed truss and fixed angle truss, but the variable angle truss. It's not that the truss is changing its angle. The cracks remain at 45 degrees, most of them. Sometimes you see some bifurcation and so on. Is the stress flow that can also pass through the cracks because of the aggregate interlock of the cohesivity of the crack and so on. So for this reason, but now I must be able to go back. Okay, very nice. For this reason, you see, you have in the formula this, angle here, cotangent of theta. That angle is exactly the inclination of the strut, which takes into account initial 45 degrees plus this flattening effect, let's call it like that. Well, the issue is, how do I quantify this angle? Well, first thing is this. In the codes, you find that you must provide a minimum shear reinforcement, unless you use fibers, but that is another thing. Minimum shear reinforcement, the formula is this, and this rho S web is the area of the stirrups divided by the spacing. Okay? So with two 8mm stirrups, one per rib, we are okay. And we decided to put them every 300 millimeters, every 30 centimeters. That is an easy way. Basically, you put 3 stirrups per meter, that is. So we comply with that. This is not very shear sensitive structure. For this reason, you just need the minimum reinforcement anyway. But then with this value, okay, you end up with something. How do you estimate theta? Well, in the codes now, there are some relationship, and it's written, it should not be higher than 2.5, because what does it happen? 2.5 means that your angle, the cotangent of theta should be 2.5, not higher than that. Means that your angle should not be lower than about 22 degrees. This is more or less. 22 degrees is a very low angle, very low strut. If you go lower, in order to exploit those aggregate interlock, it means that your beam must deform too much. So if you go lower, it's true that your shear capacity increases, but your beam is so sagged that you have lost. So that is the reason for it. But in pre-stressed concrete, we can calculate the angle in this way. First of all, where do we calculate the shear force? Because the shear force is maximum at the support, and it's equal to the total load times L half. But why do I put here L half minus D? So I am not calculating at the support axis, I'm staying a little bit inside. Well, this is because since the shear model works like a truss, the support from the reaction goes inside with a truss inclined at 45 degrees. So the critical region is at half of this strut. So just let's see. This is your element, and this is your support. So this is the support axis. The reaction force, which is here, it goes with this stress flow. Okay, and if this is something like D, this distance here is also something like D. So what we generally do is that we put at half of this distance, because that is the first critical section for the shear. Just allow you a slight saving in the shear action, because as long as you move inside, your shear force is a little bit less. D is the effective depth. Yeah, you go inside from D. This is D, and you go inside of the same quantity. And you go inside of, oh, okay, you can put it here as well, yeah. Yes and no, in the sense that that angle, why it's happening? It's happening because the beam is deflecting, but close to the support beam, so it's rather a rigid part, so you just move that. So at this position here, you have not the full pre-stressing force, but you have a part of it because of the development length. And if this length is 0.45 or whatever, it means that we have about 25% of it. So at this cross section here, you have a shear force, but you have also the pre-stressing action, 25% of it. So on the centroid, on the neutral axis, the sigma is non-zero. The sigma is a compressive stress due to the pre-stressing force. So you have a situation which is like this. It's not pure shear, but it's pure shear plus some compressive force. So your first cracking angle will not be 45 degrees. It will be different. It will be already a little bit lower because you already have the compression stress, which alters that. So what we do, and if you calculate the cotangent of this first cracking angle with the Mohr circle, it turns to be not 1. Cotangent of 45 degrees is 1. In this case, it's 1.25, which you can see it's probably an angle of around 40 degrees or something like that. You already have an initial lowering of the angle because of the pre-stress. What do we do to stay on the safe side is that we allow from this initial angle to go lower in such a way that the cotangent is the initial one plus 1. Which turns out to be 2.25. And we are, with 2.25, the code states not higher than 2.5. So we are in a, safe or allowed region. And obviously, when we check a truss, the truss is made by two elements. Which are together carrying the force. So the resistance of the weakest element gives you the strength. And here you can see that this is these are the code formula developed according to the truss model. I'm not going to explain them, but this is the strength on the steel side, and this is the strength on the concrete side. And generally, we avoid over design. You see that here the strength on the steel side is the lowest one. So it means that if it's going to fail in shear, the steel will fail, which guarantees you some ductility. And also you can see here the safety factor that you have is 2.29, 230 divided by 1.25. So it's about 15% or something like that. So it's higher than the safety factor that we have on the moment. This is important. This is important because even if the failure of the shear is governed by the steel, so by the ductile part, shear is always a brittle mechanism. Bending is a ductile failure mechanism. So if the safety factor of the bending failure mechanism is lower than the safety factor of the brittle failure mechanism, it means that wherever it will happen, the ductile mechanism will occur first. Ductile mechanisms occur with large deformation, so give us a warning. Brittle mechanisms occur without a warning, so we want to avoid them. This is in the way, it's not exactly the capacity design, But these concepts are those which inform the capacity design as well. So in some cases, we over-designed the brittle mechanism so that the ductile mechanism, of course, works. But this was not the case. Then there is one last thing. We are almost over. Yeah, there is one last thing that I want to explain. You see here, sorry, here there is another misprint. This is FCD. Okay. But as you can see there is a factor that is a Greek letter ni. So we apply a reduction factor for concrete in the truss mechanism. And in the code, you have this, formula to calculate it. Why do we apply this reduction mechanism? Well, because imagine this is your beam. And you have your stirrups. And you have you have also your longitudinal reinforcement. You have something here, you have the cracks. So your strut is something in between the cracks, which is experiencing these aggregate interlock forces, but which is also experiencing stresses transmitted by the stirrups, which are tensile. So it's like if you single out an element, imagine that you try to single out an element of concrete from here. This element of concrete is experiencing some compressive stresses, but is also experiencing in some way some tensile stresses in the transverse direction. These are transmitted by the stirrups and other mechanisms. So in the strut, in the inclined strut, the concrete is not experiencing a uniaxial stress of state, is experiencing a multi-axial stress of state. And as we will see tomorrow, multi-axial stress of state, if they are compression, they can be beneficial. But if they are compression, tension, they are not beneficial. Because when you compress a material, it tends already to expand by Poisson effect. If you have a tensile stress, that tensile stress is accelerating the failure. So that is the reason for which in the shear formula for the compressive strut, we have this ni factor, which is a reduction factor. And this comes from, Professor Aslan knows very well, this comes from studies which were done at University of Toronto and University of Houston. With the panel tester, they tested slab elements in concrete with reinforcement and so on under biaxial stress states to derive constitutive laws of concrete in one direction as a function of the state of stress and deformation in the other direction.